We are now discussing thermodynamics, chapter 1. In the last class, we have seen what is meant by temperature, what are the different scales of temperature, and how you can convert from Celsius scale to Kelvin scale, and from Kelvin scale to Fahrenheit and all. Now, today, we will see why do we require thermodynamics? Why do we need a branch of physics called thermodynamics? This is because to make our work easy, sometimes we have to convert heat energy to mechanical energy. And sometimes we will have to convert mechanical energy to heat energy. So there are certain laws in thermodynamics that will explain to us how we can convert mechanical energy to heat energy, and also how we can convert heat energy to mechanical energy. There are several heat engines and refrigerators. In fact, the development of heat engine have revolutionized the world of physics. So that is why we are learning thermodynamics in detail. So while going to thermodynamics in detail, there are certain terms which we have to explain. So the first term which I want to explain today is the mechanical equivalent of heat. Mechanical equivalent of heat. What is the unit of work? Joules. What is the unit of heat? It's also joule, because work can be converted to heat, or heat can be converted to work. Heat is yet another form of energy. So heat energy also has the unit of energy, which is joules. So mechanical equivalent of heat means the amount of work required to produce unit amount of heat. Suppose the work done is W. W is the work done. And the amount of heat produced is H. For a simple example, let me just rub my hands together. After some times, I'm feeling hot. You can try that yourself. So this is a mechanical work done, and what is produced? Heat is produced. Otherwise, you can see any machine which works for a long time, after some time, it gets heated up. So any mechanical work, if it is done for some time, it gets converted to heat. So the amount of work done to produce 1 joule of heat is called the mechanical equivalent of heat. So let me tell, work done, W is equal to a constant, or I can tell that if we do more work, more heat is produced. So work done is directly proportional to the amount of heat, or work done is equal to a constant into heat, and this constant is called the mechanical equivalent of heat. So the mechanical equivalent of heat is equal to work done by heat produced. So if H is equal to 1 joules, W will be equal to J, right? If H is equal to 1, J will be equal to W. That is why we are defining the mechanical equivalent of heat as the amount of work done to produce unit heat energy. Can you guess what will be the unit of mechanical equivalent of heat? Will it have any units? No, because this is in joules, this is also in joules. So the dimension of mechanical equivalent of heat is not there. Now, there is another way we interpret that. Earlier, heat energy or the energy was measured in calories. Even now you can see in some food packets, the amount of energy is mentioned in calories. So whenever we mention work done in terms of joules and the amount of heat in calories, sometimes the unit of mechanical equivalent is mentioned as joule per calorie. So this is one of the unit of mechanical equivalent, but both work and heat energy has the same dimension. Therefore, the mechanical equivalent of heat doesn't have any dimension, but when we use the old concepts of units, where heat energy was measured in calories, we call that the mechanical equivalent of heat has a unit joule per calorie. And what is the value of this mechanical equivalent of heat? It's a constant value. Do you know the value? It is 4.2. So you have to remember the value of mechanical equivalent is 4.2. Is it clear what is meant by mechanical equivalent of heat?
Yes.
Okay. So that's all I wanted to explain about mechanical equivalent of heat. Now, how can we define or how can we completely state the position of an object in space? How will we state the position of an object in space? How will we tell it? How many coordinates are required? To completely mention the position of an object in space, we require 3 coordinates. So we will tell how much it is along the x-axis, how much along the y-axis, and how much along the z-axis. Similarly, if there is any state of a matter, for example, you have water. Water is in water vapor. We expect that the water is in water vapor state at 100 degrees Celsius, right? Can there be any situation where the water can exist at 102 degrees Celsius and it is not in the vapor form?
No.
There is. Do you use pressure cookers at home? Why do you use pressure cookers?
For
If you
the
are
vape,
cooking dal, it's better to cook in pressure cooker, right? Why?
it cooks fast.
It cooks fast. Why? Because in pressure cooker, the pressure is so high. When the pressure is so high, the boiling point of water is above 100 degrees. So the water inside the pressure cooker can stay in the water state itself, in the liquid state itself, even at higher temperature. So the water inside the pressure cooker may be at 104, 105 degrees. It can be. So at high pressure, the boiling point is different. So when we say water, if we just tell the temperature of it, is it enough? No, we need to mention at what pressure. Also, when you go to high altitude, for example, in my country, one of the high altitude places are Ooty. When we go to Ooty, it's very difficult to cook there in open pots because it's at high altitude. So the pressure is lesser than the sea level or ground level. So the temperature required for water to boil is less than 100 degrees. So when we boil something, you will not get water at 100 degree. It will be below. Before 100 degree, it will have evaporated. So we need to state both pressure and temperature, and there is one more quantity called volume. So just like we need 3 coordinates to exactly tell what is the position of an object, we require 3 coordinates to tell the thermodynamic property of a system. So these 3 properties are called the thermodynamic coordinates. So what are the thermodynamic coordinates? Thermodynamic coordinates. Thermodynamic coordinates are temperature, pressure, and volume. These three are called the thermodynamic coordinates because we need to specify the temperature, pressure, and volume to completely explain the thermodynamic property of a system. Now let us see what is meant by a system. I'm telling system, right? So what is a system? System is something about which we are studying. For example, we are taking a vessel containing some water and we are heating, we are learning its properties. So that vessel containing water or the water is the system. So it's that part of the universe or the environment which we are concerned about while studying thermodynamics. That's called a system. And systems can be of different types. So the systems can be open, the system can be closed, or the system can be isolated. Now, what is the difference between an open system, a closed system, and an isolated system? So, a system can be either open, closed, or isolated. When do we say that a system is open? We say that the system is open if it can exchange with its environment, that is the surrounding places, if it can exchange with its environment both mass and energy. So in open system, mass is exchanged and energy is exchanged. Both of them are exchanged with the surroundings, exchange with environment. Okay, so in an open system, both mass and energy are exchanged with an environment. For example, if you have a vessel containing water and if it is heated and there is no lid over it, it's an open system. For example, if you are boiling water for tea, it's an open system. If you are in a lab, you are just heating some liquid, oil for example, it's an open system because the water can, if you are boiling water, the water can become vapor and it can go to the surroundings. So its mass is exchanged with the surroundings. And also when it gets heated, it's open and it's in a normal metal vessel. So the heat energy is also exchanged with the environment. So in an open system, both mass and energy are exchanged with the environment. And example is just a vessel containing water without a liquid, which is just heat. So it can exchange both its mass and energy with the surrounding. Now, what is meant by a closed system? In a closed system, mass is not exchanged. Okay? But energy is exchanged. Energy is exchanged with the environment. So both, it's not about both mass and energy. Only mass is not exchanged with the environment, but energy is exchanged. How can we make this open system closed? I told this as an example where in a vessel, water is boiling. We have applied heat. I'm not very good at drawing, but with explanation, I hope you can understand. So what should I do to make this a closed system? Just put a lid over it. If you put a lid over it, the water vapor cannot go out, right? Suppose you are making dum biryani. If you are making dum biryani, you will cover the top and seal it, right? Why? The vapors should not go out. It should all come into the food. So that's a closed system. But you are boiling that in a normal vessel, normal metal vessel. So the heat energy can be exchanged with the surroundings. So it's an example for a closed system. The mass will not go out, which means the vapors will not escape, but energy, the heat energy in the vessel can be exchanged with the surroundings. That's an example for a closed system. So to make this open system closed, what you have to do is you just have to put a lid on the vessel. So in that case, what happens is it can exchange heat as radiation to the surrounding, but there is no exchange of mass. Now, what is meant by isolated system? Can you guess now? In open, both mass and energy are exchanged. In closed, mass is not exchanged, energy is exchanged. What about isolated system?
Here, mass and energy, both of them are not exchanged.
Yes, both mass and energy are not exchanged. Can you give me an example? Can you give me an example where both mass and energy are not exchanged? Do you have a practice at home of pouring tea in a thermal flask and keeping? If you,
Yes.
yeah, if you keep the tea in a thermal flask and keep it there, what will happen? It won't lose heat, right? So both the vapors, the mass cannot escape into the environment and also the heat cannot escape into the environment. That is one example, a thermal flask. And another example is, have you seen where people keep ice in a thermocol box? You may not have seen much, but at my time when I was a student at school, people used to sell ice in a cycle. So they make a bell and we run towards them. They keep a thermocol box with a thermocol cover. And all the ice will be kept inside and it will stay ice. It will not melt because thermocol is an insulator for heat energy. So here the heat energy from outside cannot get into the thermocol box. Also, we have seen in my country, my place, even now, when they sell fish in the morning, they keep fish and put some ice and they keep that in a thermocol box and sell. So the heat energy is not escaped to the or heat energy doesn't come in and spoil the fish. So these are all examples for isolated system where both mass and energy are not exchanged. Is this clear to you? What is meant by a system and what are the different types of systems?
Open, closed, and isolated.
Excuse me, I didn't hear you, Hasina.
The different types of system, right? Open, closed, and isolated.
Yes. Is that clear to you? Is the concept clear to you?
Yes, teacher.
Okay. So now let us see another term which is also related to thermodynamics, which is called the internal energy. Internal energy of a system. What is meant by internal energy? We know that all matters are made of atoms. Atoms combine to form molecules, and atoms themselves are made up of subatomic particles like electrons, protons, and neutrons. You know that the electrons are always moving, they are revolving around the nucleus. And these atoms, which are part of molecules, are vibrating. Suppose it's a water molecule. It contains hydrogen atoms and oxygen, right? So they are bonded together, but they are not staying, they are not just static, they are vibrating. Even within the bones, they are vibrating. And as a whole, the molecules inside the matter, they will be revolving vibrating and all. And that's true not only for gas molecule. Gas molecules, they have more freedom to move around. They are freely moving. The gas molecules are freely moving. And when we come to liquid molecules, they can also flow and they can fill in the vessel where they are, and they are also complete undergoing vibration. Even if we take a piece of solid, the molecules inside that solid and the atoms, they are in vibrational motion. So when we discuss the motion of molecule or matter, everything inside the matter are either moving from one place to another, which is called translation, or they are rotating, or they are vibrating. So the energy of all of this together is called the internal energy of a system. So internal energy of a system is the energy of translation, rotation, vibration of all the molecules, atoms, and subatomic particles inside a system. So when you are asked what is meant by internal energy of a system, you have to tell internal energy of a system is due to all kinds of motion. That is translation. If you consider gas molecules, they have translation, then rotation. When you consider gas and liquids, both have rotational motion and vibration. So it's due to translation, rotation, and vibrational motion of what all things can be there in a system, which is any matter. There can be molecules, there can be atoms, there can be subatomic particles. Atomic particles. So it's due to the translational, rotational, and vibrational motions of all molecules, atoms, and subatomic particles in a system. So that's called internal energy of a system. Is there any means to find out the total internal energy of a system? No, we cannot find out the total internal energy of a system. So that's not an important quantity. What is important is the change in internal energy of a system. For example, if you are heating a liquid, what will happen? What will happen to the molecules' motion? Will they move more or less? They will move more, because when you heat, what happens? The kinetic energy of the molecules will increase, right? So they will move more. So that is one way we can increase the internal energy of a system. Even if you take gas in a closed container and if you heat it, the gas molecules will move more faster and their kinetic energy will be increased. So when you increase temperature, what happens? When you heat a system, its internal energy increases. Now what happens when the system cools down? What will happen to its internal energy?
It will reduce.
It will reduce. So when a system cools down, its internal energy reduces. So that's what is important, the difference in internal energy of a system. And it is very much related to the temperature or the amount of heat given. So that is another concept which is important in thermodynamics, internal energy of a system. So you should know what is internal energy of a system and how it can be changed. So if you heat, it increases, and if it cools down, it decreases. And it's not the absolute value of internal energy which is important, but it's the difference in internal energy of a system that is important. Now, we have learned some terms related to thermodynamics, and let us go to the main content, which are the laws of thermodynamics. So we will discuss today the first law of thermodynamics. What is the first law of thermodynamics? The first law of thermodynamics states that if you give some energy, some heat energy to a system, a part of that energy is used to raise its internal energy, and a part of the energy can be used to do external work. So when you state that first law of thermodynamics, the language of physics is math. So any physical law can be best expressed in the form of an equation. So is the first law of thermodynamics. So we can state the first law of thermodynamics in words as well as in an equation. In equation form, you can express it as delta Q is equal to delta U plus delta W, where delta Q is the amount of heat given. So what is delta Q? It's the amount of heat given to a system. So delta Q is the amount of heat given to a system. What happens when we give heat to the system? Its internal energy will increase, right? So delta U is the change in internal energy. Internal energy. Okay, so U stands for the internal energy. Delta means the change in internal energy. Now, what is W? Work done.
Work done.
Yes. So, delta W is the work done by the system. Work done by the system on the surroundings. So, this is the mathematical statement of the first law of thermodynamics. It states that if we give some heat energy to a system, a part of it is used to raise the internal energy and the other part is used to do work on the environment, means on its surroundings. So, work, and there are certain conditions where each of these quantities will be positive or negative. So the amount of heat given can be positive if heat is given, and it can be negative if heat is taken away. So heat is given, then it is positive. So positive if it is given to the system. If you give heat, then it is considered positive, and it is considered negative if heat is taken. How can we take heat from a system? Okay, I have a vessel containing water. How can I take heat from it? There are no means to take heat. You can give heat, just heat it up. Just keep it on a heater. But how can you take heat from a vessel of water? You can keep it in a refrigerator, or you can put ice in it, or you can put any cold metal spoon or something in it. So what happens? By thermal equilibrium, heat energy will flow from the hotter body to the cooler body until both of them have the same temperature, right? So if you put a piece of ice in it, what will happen? Heat energy from the water will go to ice, and until both of them will get the same temperature. So that's how you can take heat from a system. So if the heat is given, delta Q is positive. If the heat is taken from it, delta Q is negative. Now change in internal energy. If the internal energy increases, delta U is positive. And can you guess when it will be negative? When the internal energy
Decreases.
Decreases.
So when the internal energy decreases, delta U is negative. Okay. So what about the work done? If the work is done by the system where we give the energy. So if you are heating a gas and the gas is pushing a piston out, work is done by the gas on the surroundings. So if work is done by the system, delta W is given by, delta W is positive. So delta W is positive if, let me just write, positive is if work is done by the system. Okay. Now, if work is done on the system, it is negative. On the system, delta W is negative. For example, as I told before, if you take a container with a piston, and this container has gas. Then if you are heating it, what will happen? The gas will expand and the piston will move out. So work is done by the system. Then we can tell that delta W is equal to positive because work is done by the system. The air is pushing the piston out. So it's doing work. Now, instead of heating that, if you are pushing with your hand the piston in, you are doing work on the system. In that case, delta W is taken to be negative. Now, don't get confused at this stage with what you study in about thermodynamics in chemistry. You must have learned the first law of thermodynamics in chemistry as well. But here, the concept is taught different, slightly different. In chemistry, they take the work done as positive or negative in the opposite way. So don't get confused. Always remember that in physics, work done is considered positive is if work is done by the system on the surroundings. And if it is considered negative if work is done on the system by the surroundings. Is that clear to you? The first law of thermodynamics, is it clear to you? The statement, the equation, and when they are considered positive and negative. Is it clear?
Yes, teacher.
Okay, now in next class, we will see different processes, thermodynamic processes like isobaric, isochoric, adiabatic and all, and how the first law of thermodynamics appears in each of these processes. Okay,